thing we're going to look at is something we already know, but they're returning to it because we've already talked about it. We're going to look at the velocity and acceleration function. Does this thing look squinty to you? Because it feels squinty to me. I wonder if I'm... Hey, that's worse. Okay, we're going to find velocity and acceleration of space curves. Second thing is we're going to find how to get a space curve. When you're told either the velocity or the acceleration, and some initial data. And that will be essential integration. And the last thing we're going to do is we're going to find some guys called the tangential component of acceleration and the normal component of acceleration. And evidently these things are important to I'm not sure it's the physics, probably the physics people, who are interested in the motion of three-dimensional objects. I'm assuming here, I don't know a lot about this topic as far as practical parts go, but I'm imagining that people who model spaceships moving in 3D or asteroids traveling through space or anything that's three-dimensional, you know, moving in 3 dimensions, that they would want to know things to do with velocity and acceleration, and I forgot one here, and speed. And 3, it's quite interesting that you know the acceleration of a 3-dimensional object is actually a linear combination of the tangential and normal components, which is if you use as your vector basis, in other words, if you use as your axes instead of some arbitrary X, Y, and Z, but if you use as your axes the direction that the tangential is going as 1, the normal is going as a 2nd, and the binomial is going as 3rd, that is actually a more realistic what's the word? A more realistic vector space, a more axes to use. You would typically probably do it at the origin of the object, and then everything else would be given in terms of those 3 vectors. And that can often lead to simpler results. You know, in space there is no origin anyway, so you can put it anywhere you damn well like. But X, Y, and Z can be quite arbitrary, but unit tangent, unit normal, and unit binormal, because they are all orthogonal to each other, they're just like taking your XY axis and rotating it a little bit and sticking it down. So that's kind of cool. And this thing here, for its own part, is quite nice. What I'm hoping is, because I'm going to pick them, is that the math involved is going to be a lot less tedious than unit tangent, unit normal, unit binormal. Mostly because you have to do less work, at least for these 2. This one here, this one here is probably going to be as messy as yesterday's, but these 2 should be fine. Okay, so let's look at the first one. How to find acceleration vector, velocity and speed, no particular order. Well, I'm going to start with my favourite function. Do you know who my favourite function is going to be?
Is it a helix?
It is. And I think the book also realises that helixes just tend to play well with a lot of space curve questions, don't they? Even unit tangent and unit normal. So it's not a surprise I'm going to go here. I'll try and mix and match a little bit. How about -3 the sine of 2x, 1 plus 3 times the cosine of 2t, and 5t. So let's suppose our question was, and they do actually have them, homework questions I had a quick scan through, and they say things like, here's your space curve, find the acceleration vector at t, the velocity vector at t, and the speed. Actually, in the order that you should do them, shouldn't you find the velocity first? Oh, by the way, if I write down v with nothing and v with brackets t, do you know it's exactly the same thing? Just convention that, you know, you don't always need to write it because we know that it's there. So the velocity vector then, you differentiate this guy, you will get -6, the cosine of 2t. If you do the fella next to it, I believe you get -6, the sine of 2t, and if you do that guy, you get 5. And the good news is that's it finished. Now, a lot less work than what you've done before, and we have seen this stuff, so this is just more practice. Now, if I want to get the acceleration, isn't the acceleration just the derivative of the velocity vector? So I just differentiate it again, and that's going to get me a +12 sine 2t. This one's going to get a -12 cosine 2t. And this thing is going to get me a big fat 0. So as long as you know how to differentiate, you just do it 3 times, you've got the velocity. You take the derivative of those guys 3 times, you've now got the acceleration vector. Suppose you want speed. That's speed, isn't it? It's the magnitude of the velocity vector. And to get that, we do the square root of this guy squared, middle guy squared, last guy squared. That guy's going to get me 36 cos squareds. Then I'm going to get 36 sine squareds. And then I'm going to get 25. And we've seen enough of these guys, just that it becomes second nature. You agree those two guys get me 36. Add another 25, 50, 61. I don't think I know any common factors that are at least obvious to that. So that's probably my final answer then, right? And evidently, when you're moving along this type of helix, aren't you traveling along the roller coaster of death at the square root of 61 meters per second at every point along its curvature? So it doesn't actually, at least in this question here, the helix has a constant speed, doesn't it? And its velocity and acceleration vector. I kind of like questions that are straightforward. Would you agree, as long as you know how to differentiate and you do a lot of it, you'll be able to get velocities, accelerations, and speeds. I don't think the homework goes into that, but just for completeness sake, I want to include that. Do you know that you could have been asked to find velocity, acceleration, and speed at, say, t equals pi? You know, at some value of t. You do exactly what I've done here, but then when you do one extra step, when you just put in pi here, here, and here, and here and here, and that would still be the square root of 61, no matter what t is. And so you could evaluate what the velocity vector looks like, what the acceleration vector looks like, and the speed at any given value of t. Actually, since that's there, I should be able to do that relatively quickly. Cosine of 2 pi is the same as the cosine of 0, so it's 1. So that's -6, that's 0, and that's 5. So that's your velocity vector as you shoot off to your death. Right? Remember, velocity vector is the same as the direction vector. Now, what's your acceleration going to be? Well, at pi, let's see, that's going to be 0. That's going to be -12, and that's going to be 0. And your speed is going to be that. So at one particular point, in this case, at t equals pi seconds, that will be the vector that says the direction you're moving, your velocity vector as well. And this is your acceleration vector, and this is your velocity vector. So actually, at that point in time, aren't the x and y components of your direction not going to change in velocity? And isn't the x and z, isn't the y direction of your movement got a negative acceleration of 12? So it's pulling back in the y direction for some reason. So we pretty much know everything you need to know about a moving object if you tell me this one. Now I'm putting this one also in only because it's good to tell you stuff even if it's not a testable thing. If we start with our space curve, we already know that the first derivative is called the velocity vector, right? And we know that the second derivative is the acceleration vector. Did you know that sometimes they use third derivative? Third derivative is what? The derivative of the acceleration vector. And it has a name. Does anybody know what that thing is called?
Is it jerk?
It is. And the person who came up with that name was probably one, but never mind. That is it. As far as I know, there is no special names for fourth, fifth, and sixth derivatives. They probably didn't get special names because they're not used at all, or so rarely used, it's not worth talking about. It's not worth giving something a name if you use it once in a blue moon. Does anybody have an idea? And this is me asking a question that I don't know the answer to really. What, I know what velocity does. I can imagine velocity, right? I'm thinking 2D world on the road, but I can do that. I can even figure out what acceleration is, right? I got a feeling for, you know, increasing velocity through time or rate of increase, things like that. But what does jerk tell you?
Well, it would be the, you know, since the derivative is rate of change and it's a rate of change of acceleration, jerk would probably be the kind of the change of acceleration being the forces exerted on you to cause acceleration to change, or at least be some measurement of that.
Right. So, I mean, from that everything was a rate of change of the thing before it. I'm just wondering if you were in an object that actually was not 0, 0, 0, right? That actually was something. Do you know when there's a phrase that I'm thinking it might be coming from, and I hope someone was saying, yeah, that's it. Can you imagine that you're driving along and then suddenly some change happens to your movement and you feel a little jerk, you know, like I get a jerk to my chair? Is it that kind of jerk? Is that what you would feel?
So I Googled it and it just says the rate of change of acceleration with respect to time.
So it doesn't give, I'm trying to imagine what a moving object's, what the jerk would feel like if a moving object had some. But evidently it doesn't have any specific meaning, so I guess that's it. Somebody must use it, right? Or else it wouldn't even have a name. So maybe it's used for special cases. Right, so kind of pausing back for a minute. If I gave you a velocity, if I give you a space curve, and I'm going to do 2 more examples, and then hopefully we'll call that a day as far as this goes. If I gave you a space curve, do you feel comfortable how you get velocity, acceleration, and speed? Right, first derivative, second derivative, do your stuff, and magnitude of velocity vector. And that's about it. Okay, well, That came out quite nice. Here's my second example. This one, I'm going to do a polynomial. Basically, just all three terms are going to be various power or powers of t. So this one's going to be 2t squared plus 1. This one's going to be 6t cubed. And this is going to be 4t minus 1. Now, I just randomly chose those digits, so I do not expect anything particularly nice, to come out of that. But that's fine. The velocity vector then, won't it just be 4t, 18t squared, and 4? You agree? And the acceleration vector is 4, 36t, and 0. I mean, you couldn't get much nicer than that. Helixes are nice, but a little bit messy. Isn't this nicer? There's not really a lot of brain power needed to differentiate powers of t. And to get the speed, it's just simply going to be that guy squared, this fella squared, plus that guy squared. And this is going to be 16t squared. I'm not even going to attempt to do 18 squared in my head. 324 t to the 4 plus 16. And this is really just cosmetic. Now I know, because I randomly choose chose the things up here, that this guy, although he is 3 terms, it would be a miracle and a half if this one was a perfect square. In fact, looking at it, would you agree it ain't going to be a perfect square? Right? I mean, those numbers don't look even vaguely like they're going to play well together. In fact, that number there doesn't even match a perfect square. So that's the end of that. But be on the lookout for three terms inside the square root. Because won't 3 terms inside the square root have a good chance of being a perfect square? In which case, this answer will be simplified, because if you type in this one, it will say error. And you will wonder what you've done wrong because it looks fine. Well, in fact, it does look fine, this one, right? But have you noticed perfect square algebra gets used a fair amount in the last few days? Inside square roots when you're doing arc lengths, for instance. When you were doing the unit tangent and the unit normal, when you were when you were finding the magnitude of those vectors so you could get a unit out of it, wasn't a perfect square very helpful in making that reduce? So, as a little practice, what goes here? Anyone?
Two t squared.
Okay. And I'll put the last one. Right. Now I know the right answer. I'll change the question to fit. But you put them in order, and you forget about the middle one. If it's a perfect square, you can forget about it. It'll sort itself out. But the square root of that gets you 2, half the power. Square root of that gets you 3. So anytime you see a speed question and there's 3 terms inside it, and be on the lookout for a perfect square. Even when it looks weird and wonderful, you might have already done some homework questions. Have you done ones where you looked at it and think, God, that's not a perfect square, and it ended up working? Right? So always be on the lookout for it. Right, now, third one. I'm really just going to put together the worst looking guy I can get, working on the assumption But if it's ugly and you can do it, then you can do all the easy ones, right? So each one of these three is going to have a different problem as far as derivatives go. So first one's going to be that one. Second one is going to be that one. And the third one's going to be that. So if you think about why I chose those, quotient rule, product rule, chain rule, right? I just picked them. Now I could make them a lot worse, but they don't go much worse than that. So for our last shot at this type of question, the velocity would be the derivative of this, derivative of this, derivative of this. So if you take the first one and you call this f and you call this g, then I'm going to be using f dash g minus f of g dashed over g squared. So I'm going to have 2t times t plus 1 subtract t squared times 1 over t plus 1 squared. So that's going to be 2t squared, take away t squared, that's going to be a t squared plus a 2t when I'm finished, over t plus 1 squared. So I'm going to put that one there. I may not do this one all the way to the end. This one here, and won't it be e to the power of sine t times the derivative of sine t, which is cosine t? Won't this one be a product rule? So we call this f, we call this g. The product rule would be f dash g plus f of g dashed. That's going to get me 1 e to the t, e to the 2t. This is going to get me 2 times 2e to 2t. So that's going to get me an e to the 2t when you pull it out, and a 1 plus 2t inside, and we are done. So quotient rule, chain rule, product rule. Now I'm going to do a little cheat. Right, but I will talk about them. Would you agree that if you want to differentiate this fella, it is going to be a quotient rule? It's a fraction. What do you think I'm going to have to do about the t plus 1 squared bit to make it a little bit easier to do the quotient rule to it?
U substitution?
Well, we are differentiating, so we won't do any substitution techniques.
Wouldn't you just FOIL it out so you don't have the double square?
Yeah, I'd probably do it that way. Or, yeah, that's how I would do it. I would just call it t squared plus 2t plus 1, right, and deal with it that way. If you keep it there, then you end up having to do a mix and match technique. Don't you have to do a quotient rule with a little baby chain rule inside it, kind of thing? It's going to be messy. This one here is not so bad. Would you agree this one's going to be a product rule? And the cosine t is going to be the f, and the e to the power of sine t is going to be the g, and you're good to go. And this one next to it's actually going to be a product rule. In fact, the way I've written it kind of makes it more obvious that it's a product rule. So that would be that fella. Now, oops. Speed. Well, speed is going to be the square root of first guy squared, second guy squared, third guy squared. And I mean that one's the first guy, that one's the second guy, and that one's the third guy. Would you agree that that is just pure ugly algebra and there's probably nothing good going to come out of that? So I don't expect when this whole mess is finished to have a perfect square or anything. I'd be flabbergasted if that ever happened. So as long as you know how to differentiate, you will fight your way through all of these. from what I recollect, my memory's not great. I think most of the questions that you do this to are pretty standard, you know, and are not as ugly as that. Are there any questions about finding velocities, acceleration, or speed of a moving object? Does anybody have any issues with that? Is it fair to say we can move on then? Okay. Now, we haven't done much integration. We've done just a little, so we know the process, but very, very little practice. So we are now going to do a group of questions where that's actually what you do. You integrate to solve them. So here's my problem. Suppose I have been told the acceleration vector. Try and make my life easy. And it's that. And I'm being asked to find what the space curve is, being told that the velocity vector at 0 is 0, 1, 1, and that the position at 0 is 1, 2, 3. This would be the equivalent of being told the f dashed x was x cubed, and you've been asked to find f of x when you're also told that f of 0 is 4. Do you know those kind of questions where you're told the derivative and now you're going to work backwards to the original function? So that would be the equivalent. You might have got it phrased a little bit different from the way I just said it. Have you ever, can you remember doing questions where the velocity was 2t squared plus 5t and they wanted to know the position function? And they told you that, you know, s of 0 is 4. Or they told you the acceleration was t cubed and the velocity at 1 was 10 and the position, you know, was 5. I'm looking for vague recollections of I have seen that somewhere idea. Right, we're going to do the same idea. So I'll start off with my acceleration vector. If you integrate acceleration, shouldn't you get velocity? That makes sense? You go down the way differentiating if you come up the way you integrate. So my velocity vector is going to be the integral of this fella. So it's going to be the integral of 2t e to the t sine t dt. Well, what does that get you? Well, if you integrate 2t, you get t squared plus an arbitrary constant, which I'm going to call c1. Now, if you integrate e to the t, you get e to the t plus a different arbitrary constant. Remember, you have to have a different c for each one of the 3 components. And if you integrate, this is a 50-50. If you integrate sine t, what do you get?
Negative cosine t.
Plus an arbitrary constant, which we'll call C3.
I have a question.
Yes.
In the homework, they had solve for just one constant when it was in the form of I, J, and K. So, like, rather than finding 3, we only found one constant. And
They
problem on the homework.
didn't, although I know what you're saying. Oh, they shouldn't. They may have called it the C vector. And the C vector means C1, C2, C3. Now, I'm annoyed at them because it's 3 different numbers. In fact, I'm about to find them and I'm going to prove to you that there are 3 different numbers. It's not plus 5? Because if it was one number, wouldn't you say plus 5, plus 5, plus 5? And there's no reason in the universe why these three things should be the same, right? Each one is being totally independently integrated, and so that they should generate it. So if they did say plus C, they must be talking about plus C. You won't even see the arrow. Ah, that would explain it. I'll just make an easy one. Can you imagine it was Ti, T squared J plus K plus C. The
Yeah,
plus
that's how they had
C,
it formatted.
yeah, but plus C is a vector, which means it's really got three components, which I am calling C1, C2, and C3, which is one of the reasons I hate I, J, and K. Because you don't see it that way when you write it with a big vector C at the end, do you? Well, I would have to write it that way because we don't have bold. Right? So we now agree. I just don't like the way that they phrase that. I don't know if I've ever sold that. There is no reason why you need to do. Have you noticed I always do my questions this way, regardless of how they started life? The only connection I need to do is I guess I have to be a little bit careful when I'm writing the answer into the box, because sometimes don't they want I, J, and K in the answer, and they don't want the little funny brackets, but I'm hoping that it can deal with that. Now, let's go back to the puzzle. I'll put it over here. I know this guy. And I know this guy. I'm going to put these together to get V. And I'm going to find out what number C1 is, what number C2 is, and what number C3 is. Now, it might be the number 0, but that's a number, right? It might be 1 or -1 or something, but I need to know what they are. So wouldn't you simply just replace T, because that's T, with 0? Right, so I do a 1-for-1 match. 0 squared plus C1, e to the 0 plus C2, negative cosine of 0 plus C3, and that should equal 0, 1, and 1. Now, if you match them up, to see, I can now figure out that C1 would need to be 0. If I match these up, isn't 1 plus C2 equals 1, which means C2 is 0. And if I match this last one up, that's, what's that, -1 plus C3 equals 1. That makes C3 equals 2. I now have our velocity vector. It's going to be t squared plus nothing, e to the t plus nothing, and negative cosine t plus 2. Does that make sense? That I'm using the value of the velocity function at one given point to find out what numbers C1 and C2 and C3 are, right? You have to figure out that those constants, those arbitrary constants, are a fixed number. We just don't know what that number is. But the minute you give me this piece of information, doesn't that kind of force the C1, 2, and 3 to be one specific value? And that's what I'm doing. So we now know our velocity vector, right? But I mean, that might be the question. The question might be, here is your acceleration vector, find the velocity vector. Well, we're done. But the question was, find the position vector. Well, it's a kind of, just repeat yourself. If you integrate the velocity vector, won't you get the position vector? So I now use this as my starting point. So I'm going to integrate t squared e to the t and negative cosine t plus 2. And that's going to be my position vector. Well, here goes. If you integrate t squared, you get 1/3 t cubed plus an arbitrary constant, I'll call it C1. If you do the second one, you're going to get, oh, almost missed it. You're going to get e to the t plus C2. And if you do the last one, I believe you're going to get negative sine t plus 2t plus C3. And that's going to be your position vector. And I'm now going to use the fact that at time 0, the position vector is 1, 2, 3. So this fella, it's 1, it's 2, it's 3. Right, if you plug in 0 here, you get nothing plus C1, and that has to equal 1. So I now know what C1 is. If you plug 0 in here, I have e to the 0 plus C2 has to be equal to 2. That's 1, so that makes C2 equals 1. And the last one is, if you plug in 0, that gets you 0, that gets you 0. So basically C3 has to be, in this case, 3. I now have my position function. So I have 1/3 t cubed plus C1. I have e to the t plus C2. And I have negative sine t plus 2t add C3. It's a little bit time consuming, but I don't think the process is particularly ugly. In fact, it's a bit like you do the same process 3 times, right? One for the X, one for the Y, one for the Z. So it's kind of like what you would have done way back in, you know, Calc 2 world. Right, you just integrate and then you'd find the missing constant. We're just integrating and finding 3 missing constants because we're doing it 3 times. Are there any questions about that? As a process, does that seem to be okay? Cool, I like okay. All good. So really all they're going to do, aren't they, is they're going to change these 3 guys. You're going to have to deal with power rule, integration by parts, or U subs, right? You know, I can imagine that can turn up. So rather than, well, I got a choice here. I guess it's what you want me to do. I thought what I might do is just spend some time looking at specific integrals. In other words, imagine I was just integrating one term and looking, you know, just getting you up to speed on integration techniques. Or I could basically do another one of these questions, you know, the same way. I can actually do both, I guess. Right, so do you want me to do another one of these guys all the way to the end first? Or do you want me to just go over some of the integration techniques that you may end up having to deal with when you do this process? Any preference? Say again?
Integration techniques.
Okay, let's look at that. After that, I'm going to go and look at the homework. And as we go through, if we hit a question, you say, whoa, I don't think we covered anything quite like that, we'll do it. Right? So, integration techniques. For no particular reason, I'm only putting this in for completeness sake. I'll stick a 4 in there, right? Power rule. I mean, that should be second nature. It's like 2 times 2 is 4. You don't think about it. But basically, wouldn't that be the result of that? Now, what technique will I need to use if this was one of the terms I need to integrate?
Chain rule.
Chain rule is essentially a process for differentiation.
U sub?
Yes. Yeah, the interesting thing is that sometimes you call it the wrong thing, but you know what you're doing, right? Because isn't that just a label, right? You could say I'm going to do banana method. It don't matter as long as the method is right. You can stick any label you like on it, right? So that might have been what you were thinking, Chris. although that's not the word you used. Right, in this case, U sub it is. Obviously, you have to choose a U sub, don't you? You can't just pick anything you want, only certain things make sense. Would you agree in this case, it's the cosine t? Right. Now, if you differentiate with respect to t, I'm going to get negative sine t. And different people do this different ways. I'm just doing it the way I do it. I get that. I know some of you do this UDV thing, which is fine. I just don't do it. In this particular case then, and this is how my brain works, I always isolate the dt. So when I'm finished, I just have dt here and whatever mess it is. The reason I do that is that all I need to do now is replace this piece. So let's see what we get. I get a sine t, which I'll leave for a minute. The e to the cosine becomes e to the u, and the dt gets this guy. I can then cancel these out, and it ends up being that fella, which integrates to give you that fella. Of course, that's not the final answer, and don't you have to remember to return back to the t's? And that would be a pretty standard example of a U sub. What about that guy? What technique would I use to integrate that guy?
By parts.
You got it. There are two schools of thought on U subs and integration by parts. As you see, this is the way I do it, and that might well be the way that most of you did it, but there is a UD version of that. There's also a UDV version of this fella, and there's a formula version. I use the formula version. So this may not look the way you would do this question, but it works. You basically call the first, well, in this case, I would call this fella F and this fella G, because that's going to be the, one of them has to be F, right, and the other piece has to be G, essentially. And the formula that we have, if you use a formula version, looks like this. Now, you know your midterm's coming up, so you might want to get thinking about putting together some cheat sheets, things like various formulas, right? Like, what's the formula for the unit tangent? What's the formula for the unit normal? What's the formula for finding the speed? Just have them in one piece of paper somewhere so that you aren't hunting all over, 50 pages of notes trying to find the example that did that. You'll use a lot of time up if you don't. Does anybody here do the UDV method, as I call it?
Yeah.
Right. If you were doing the UDV method, could you just tell me who the U and the DV is so that people can say, oh yeah, I know what he's doing here. So what would your U and your DV be in this question?
I would use U as t squared, dv as sine t. And a good way to remember it is just ultraviolet voodoo is.
Say that again. Ultraviolet.
Ultraviolet voodoo is a good way to remember that equation.
What's the voodoo? Just because it goes good with the rest.
Well, it's UV ultraviolet minus VDU, which is voodoo.
Oh, the whole thing is ultraviolet minus V du. Is there not an integral in here? I guess it's not.
With the integral, but yeah, it's a good way to remember the order of it all.
It is interesting. I never even bothered with that. When I was way back in the day, this is how I was taught. Sometimes the way you taught is the way you go with, because that's the one you're used to. There is totally nothing wrong with that. This looks, in my brain, this just looks weird. I don't know how else to describe it. I guess my brain just likes formula. Isn't this basically just a formula? And formulas in my brain seem to make more sense. But that's just my brain. That might look weird and strange, and I don't even want to look at that. And that's fine. Keep doing that. You do the UV, what's that? Ultraviolet voodoo. Right? And you're good. I like that. I've never heard of that. Ultraviolet voodoo. So back to our question then. So what am I going to do is I'm going to have this guy and this guy. So f of t just means that guy. Capital G of t means the integral, right? Little g is the function, g dashed is the derivative, big G is integral. So integrate that, you get negative cosine t. Take away the derivative of t squared times e big G. That ends up being something that looks something like this. Two negatives make a plus. And it doesn't matter which method you use, don't you very often have to do integration by parts twice? You have to just repeat yourself. So in this case here, that guy's finished. But this piece here is going to become my f and my g, and I'm going to have to do it a second time. So it's going to be plus f big G take away f dash big G dt. So I've got this fella. This f here is what, 2t. If you integrate that guy, you'll get a sine. Take away the derivative of this guy is 2. The integral of that guy is sine. And we're almost done. There's a negative t squared cosine t. There's a 2t sine t. And then this fella here, when you integrate it, gets you a negative cosine. So you end up with this fella, and then your C1. You can go and look online, and there are rules or formulas for doing polynomial powers with ease, and polynomial powers with sines, and polynomial powers with cosines. It's kind of like a reduction formula, which is an even more esoteric formula where you just put things in and repeat them until you get to the end. I don't like it, so I don't use it. But yeah, you can imagine if that was t to the 5, it would get really laborious, because wouldn't we have to like turn the handle 5 times before we finally popped out at the end? So maybe in a situation like that, I would bite the bullet and I'd go and look up the formula for repeated integrals and see if I could find a version of that would deal with my situation. Actually, do you know what you do in real life? When you go to Mathematica and just put it in and find out what the answer is, which brings me to a point. That's why I need to see you're working. So when midterm happens, I don't mind so much about homework. You do what you do in homework, because homework's, although you get graded for it, homework is your way to practice the skill set that you need. But in the day of the midterm, if I see a question like this and you put that into the box in the answer, no, whatever. And there's not a sign of working, I'm not giving you any points, I don't care. Because I'm just going to assume you went to Mathematica, you plugged it in and you wrote down what it said. So the midterm is online and the answers are put there, but that's just a placeholder to make my life a little bit easier. Because what essentially I will be doing is I will have your working in front of me. I will have the WebAssign results that you've typed in, and I will look at question 1 and it will tell me you're right, and I'll go over and I'll say, yep, that's the working I would expect to see for that question. I'm giving you the points. I'm going to look at question 1 and it's correct. I'm going to look for some working and there's no working there. That's a 0. Or there's working there that no way in the world would that be the working you would need to use to get the answer you said it was. In which case you're getting another 0 for that, right? Now, that might seem a bit cruel, but we're being fair here, because isn't everybody getting treated according to what they know not how they can hit buttons on pieces of software or check answer solutions to something. But there is a plus to that. Probably for most of you, in fact, hopefully every single one of you, the plus is going to be is, can you imagine you did this question, but I don't know, somewhere in your brain that turned into a half T, right? Do you know the WebAssign is going to say 0 out of 20? Because according to WebAssign, you didn't write down the right answer. Do you notice that WebAssign doesn't say you wrote 3/4 of it right and I'll give you the, some of the points? It's very, it is or it isn't. But this is what would happen. I would look at your box and WebAssign and say 0 out of 20. I would look at your working and say, come on, she did 90% of it right, 18 points. So you will get points because computers, if I just left it to the computer, apart from the fact that some very unscrupulous people would just cheat, couldn't you do almost every single question 90% right and end up with 0 in the midterm if you left it up to the computer? Because imagine every single question, you just did a tiny thing wrong, right? A little plus here, a minus there, a 2 where it should be a half. You could, that's an exaggeration, but can you see how that wouldn't be fair to you either, right? So I want to see your working to prove you don't cheat. I also want to see your working so I can give you partial credit when you did most of it right.
Not to mention WebAssign being more than a little annoying when it comes to syntax, and the last thing you want is a 0 when you doubled up a paren, or you entered in something slightly off in a like an unreduced fraction or something, and it's a blah.
Yeah, you just got a blah. We just got to live with that. I hope one day in the future that the AI, I'll call it AI, and programming will improve to the point where we could have a new version of WebAssign where they know more about math and they will be much more flexible about things like that, so that it would make my job easier, because then, it would
well, not for nothing, the
frustration.
because I used WAMAP for my Calc 2 class last quarter, and even though it's not quite as shiny with bells and whistles, and it does have its own quirks and syntax problems, I found it was a lot less stringent when it came to entering in an answer a certain way as opposed to alternate equivalent answers that in real math work, but it doesn't have the exact, I entered it this way and it's.
Well, you can see that because I'm going to be looking at your working, how that will be a much nicer place, right? So you'll be fine. If it's right, it's right.
I still have issues with WAMAP every now and then. I missed a couple points.
What? Say that again?
In Calc 2 last quarter, I missed a couple points just because I couldn't figure out how to enter.
Well, nothing's perfect, right? Nothing is perfect.
But
I don't want to shock you here, but I'm not perfect. In fact, I used to be conceited, but now I am perfect. Oh, come on, that's a good one. Right. When we were on ground, it was much more fun because I used to do my usual lie of, did you all catch that deliberate mistake? But for some reason, when you do it in this context, it's much more severe when you do a mistake for some reason. I was going to finish on one other thing here before my brain takes me away here. So everyone here has heard my sentence. When you do your midterm, if I don't see any working for that question, you are getting a big fat 0. That's the rules of the game. Now, there's a little proviso to that. Do you know some of your homework questions is which picture is which? Well, you're just going to go to the 3D software probably and draw the thing, and you're going to pick picture 2. I don't expect to see working in a situation where it's a graphical situation, right? Where if you look at the homework right now, isn't there some questions where they give you 4 pictures of what the velocity and acceleration vector would look like? I mean, it's 1, 2, 3, or 4, no biggie. When you do your midterm, you only get one answer. So you plug it in and it's good to go. That isn't a biggie, because I can imagine you did the question and then you typed in the wrong answer, right? You had it written down in this piece of paper, right? But you know, the transfer, you missed a 2 or something. And then you hit, you know, submit, and then you go, I forget it. I only use the WebAssign as my guide to look at your working. And if I see you've written the right answer in the working, but somehow it transferred to the wrong answer in WebAssign, ain't a problem. I'm giving you the 20 points because it's really the right answer, right? And that's how things are going to work. So the stress level is reduced, believe it or not, if I can see working, because you could theoretically, don't do it please, because it makes my life 10 times harder. Couldn't you theoretically just put in 42 in every single question in WebAssign and just send me the working? Right? Please don't do that.
And because someone asked, how many questions are going to be on the midterm?
I haven't decided yet. It's 3 hours, so, you know, 3 hours is a fair amount of time, but I don't do it so a typical person would finish the last question at 3 hours. We give you a little wiggle room. So I'm trying to plan it to last about 2.5 hours. One of the nice things about WebAssign is that you don't see this, but I do. When I pick a question, it tells me what the typical student, how much time it took them to do it. So when I do my test, it'll tell me for this number of questions, it took the average student, you know, 200 minutes. Well, I would say, okay, that's too long, and I'd reduce it, right? But if it said the average student took 150 minutes, I'd say, yeah, that's about the number that I'm looking for.
Will there be a time window, or do we have all
day?
Yeah,
it'll be a time window. So when you turn up at 7, I better say that a couple of times and I'll show you emails. In fact, before I forget, I'm going to write in my little pad, send out email. So I'm making this really clear. On Monday, 7 a.m. start. It has to be that because I have other classes and they interfere. At 7 a.m., your midterm is going to start, and at 10 a.m. it's going to finish. So it's a 7 a.m., 10 a.m. window. Now, you might not need it. In fact, you shouldn't need it if it works out right for you, right? Once that's finished, you will have 1 hour to upload your working onto Canvas, and I'll talk about that tomorrow, because actually we're doing a lot of what I was going to say tomorrow right now, but it happens, that's it. So on Monday, 7 till 10. And what will happen is you'll go to WebAssign and you won't see anything at 5:02, and then suddenly it'll appear. And you may have to refresh your page to make sure that you don't miss it. And then you just go in and you do what you would do in normal homework, right? There'll be questions there, you put the answer in the boxes. The big difference is working. I would do your working, answer in the box. Your working, answer in the box. So by the time you're finished, right, won't you have your working down and the test finished? And we'll talk about tomorrow how you get this written stuff into PDF form, and then how do you upload it into Canvas so I can do what I was talking about. Well, it was a lot of side issues, but that was good stuff, right? So one more time, Monday, 7 till 10. So what will happen when you're in WebAssign is it'll open up, means you can actually go in. I believe it's a little counter. If the counter bugs you, get a piece of sticky tape and stick it over the counter so you don't see it. You know, stick it on your screen. And then at 3 hours, it'll lock you out. And that's the way it works. So you've got 3 hours to do it. So let's return back to special kinds of integration. I'm not going to go through all these ones. This next batch is how would you do it, right? So here's one. Here's another one. Okay, there were just some examples that my brain came up with. Okay, if you were going to do this as one of your terms that you're going to integrate, what technique would you use to integrate that one?
The top one, I would
I'll call it number one. Number one, yeah.
I would use a trig identity to turn cosine squared into sine squared plus or minus one, I forget which one, and then factor everything through and then u sub sine. Or
Okay.
maybe the opposite. I'm trying to think.
Okay, so
I would probably make cosine u, and then that would remove a sine from the sine squared.
Yep. And then do what you just said.
Yeah.
So it's a u equals, it's a u sub. When there's an odd and an even, always pick the even one as your u sub.
Mm-hmm.
And you're going to use up one of the signs, there'll probably be a negative floating about, but there's still going to be a sine squared left, and that's where we kick in with what you're saying. Can't sine squared be called 1 minus u squared? So if you did this one, I believe it would end up looking something like this. And then you you know, multiply it through and do your stuff.
Yeah. Just got it mixed up a little bit. But.
Nah, that's fine. Sometimes, have you noticed sometimes mathematics is more visual than verbal? It's hard to say it. It's much easier to do it.
Mm-hmm.
Yeah, just the way it is. What about this fella?
U sub again, everything under the square root.
So everything inside it, that one?
Yep. So
Yep.
e to the t plus 1.
Okay. Would you agree this is another u sub?
Yep.
Right. Oh, I should put in another one because I seem to be doing a lot of u subs. There's a special one. Log t. How on earth do you integrate just log t?
Do your ultraviolet voodoo again.
Oh, okay. In which case you have to do 1 times log t, so you have 2 functions. Great. That would work. Don't quote me on this, but I believe the answer is that. And if it's not that, I think it's actually that, now I think about it. But whatever it is, you get it. What about this fella? What about this guy?
Integration by parts.
Okay, ultraviolet voodoo. Pretty cool. So you're going to do a lot of integration. What I'm going to do now is we're going to look at the, excuse me, we're going to look at the homework and have a quick scan through. There's one last thing that I haven't done on my list, which is called the normal and tangential components of acceleration. So once we get to that part in the homework, I'll know that that's everything that we've done. Anything in chat I should worry about? Yeah. Okay, so let's, where the heck am I? Okay, someone was being helpful to one of our students, so that was nice of you. Where the heck are you? Are you here? Okay, you're looking at Cengage page right now. Shall I need to go in and out, or are we good? Right, so I'm now going to go in and look at our last, because chapter 13 is what your midterm is up to, right? So it's pretty cool. Let's see what's here. Are you looking at the homework, or will I need to go in and out? Okay, it's that. It seems to do that. You can or can't see it?
We can.
Can.
Yes, we can.
Oh, you can? Oh, I
Yes.
went out and in for no good reason then. You can see it now because I've just went out and back in. Right, so here we go.
Yes.
here is a space curve. It's written in that IGI notation. If there isn't a K, doesn't that mean there's a 0 there? I believe the rule is that when it's written as I and J's and K's, the answer needs I, J, and K's. So as you were saying earlier, Edward, it can be really weird about that. I think I've mentioned this before, but you do not write 4i. That's a keyboard I. You write 4, go over here to vectors, I. An annoyance, an awkwardness, whatever you want to call it, but that is just what you have to do, right? So if the information is in IJK format, I think we should just play safe and give the answer in IJK format. If it's in, do you know the bracket one, the one I prefer, you can do that. I don't get to do with that. Will it take both formats? Can you do IJK or you can do the funny little bracket? Will it accept both if the things are the same? Has anybody done it one way and it said no and had to do it the other?
In earlier homework, it wouldn't take both.
Right, so if it's IJK, you must go IJK, and if it's funny little brackets, you must go funny little brackets. Can you imagine then that in an exam situation where you're stressing out that you might forget? But because I will see you're working, can you see that won't make a darn bit of difference? Right, so you're stressed enough without being overwhelmed with, oh, what format do I need to write this so that it's going to give me the points, right? Just get the answer and let me figure out, is your answer the equivalent, okay? So we've covered that, right? Here's a thing, find velocity, acceleration, and speed. And they have a little sketch thing. You know, you could just plug them into the some software and see what they look like. Pretty much a polynomial, pretty straightforward. Polynomial again, helix, of course they'd have to be a helix, right? There's a helix one. Do you know your midterm questions are going to look just like these guys? Right? I don't suddenly out of the blue pull out, you know, some weird combination that you probably haven't seen. This one here looks downright ugly. But it's really just differentiation with various powers of E. There's a log with
Professor?
some stuff. Yes.
Somebody in the chat asked, are we going to be in a Zoom meeting during the midterm, or are we doing it completely on our own?
Whoa, that is a cool question. Well, I know the answer. I'll tell you now. Do you know most of what I've said now? I'm going to do it tomorrow because John Smith is missing today. I'm just making that up. And if I just assume that you all know it, isn't John Smith going to turn up at 7:25 and have lost half an hour in his midterm and doesn't know what the heck is going on because we've covered it? So I'll say it now and then hopefully I'll remember. The question is there a Zoom lesson? There will be an open Zoom lesson. And so let me see you so I can make sure your big brother's not next to you, you know, over your shoulder, pointing at the test paper and telling you what to do, or your big sister or somebody. So yeah, I'd like to see you. That would be a good verification of that. Plus, if you come across a question that is just downright weird, I'll be here. I won't really be, I'll be doing something. I'm sure I can find stuff to do. And you can just come in and say, I'll mute you all, but then you can just come in and say, hey, Mr. Robertson, question 8 of the test doesn't work, or question 8 in the test has a hyperbolic sign in it. You told us we weren't going to have hyperbolic signs, right? That kind of thing. And I'll go, oops, and I can fix that on the fly pretty quickly. Right. So that's what I'll be there for questions, and there to keep an eye on you, to keep it, you know, keep it fair. Right, are we comfortable that, sorry, Justin?
I was just saying, sounds good. Thanks for answering.
Not a problem. Right, I keep making assumptions and I hope my assumptions are right. Would you agree that these questions here are pretty much bread and butter questions? There's nothing weird going on. It's just differentiate me, and find the magnitude of the velocity vector, right? Good standard, nothing scary. I wish it wouldn't do all this IJK stuff because I like my brackets and they don't, but that's me. In fact, if you're doing the midterm and you like doing brackets as well, well, you just do brackets. You know, the little funny brackets, you know, that's fine. I'm going to give you the points anyway, right? I'm the guy that's marking it. Okay, now, starting at question 8, can you see that they've got, here is the acceleration function, which is that guy, and your answer is going to be this guy. Hold on a second, looks like my dogs are asking for something. What's up? Oh, okay. My poor wife is not well today, so she normally would do the dog poo walk. So can you forgive me for 5 minutes? I will go and give them their poo walk, or else they will bark outside for the next 2 hours because they are stubborn. And when I come back, I'll continue with it. Come on, you little buggers. All right, sorry about that. As I was saying, my wife is not getting well. She would normally be the one that does that. And just to share some things with you, the one that makes all the noise, if you hear, is her. We have a doggy door and a walk around deck. So, I mean, if they really need to go, they should just go out, walk around the deck, and they're into our yard, and there's no problem. Except that's not how she poos. I have to take her out the front door, and she has to poo in the front yard. How? Nobody understands dogs' brains. I mean, she's just weird. But we love her to death. So where was I? Yeah. Can you see question 9 is, here is the acceleration and work backwards to get the space curve. So that's what it would look like. Can you see this guy here is basically saying the velocity vector at 0 is, what's that, ijk? Isn't that 0, 0, 1? And in this case here, isn't the position vector at 0, 0, 1, 1? And those two guys, won't they allow you to find the missing C1, C2s, and C3s that we did? That seem straightforward? There isn't an awful lot of frills in here. They have a part here that really isn't a question because there's not a box there. But, you know, if you want to see what these things look like, you can certainly put them into GeoBra or some of the online graphing software. Desmos is another example of that. And you can have a look at it. But that's not a biggie. Oh, I haven't done 10. Well, there's always a question I might miss. Right. In question 10, you are given a position function, which is basically a polynomial, and you've been asked for the minimum speed. Oh, wait a minute, didn't I cover that? Well, that would have been yesterday, wasn't it? So, okay, I don't need to worry so much about that. Don't you just find the derivative and then you get the speed by the usual way, right? The square root of the thing. And then you just try and minimize it. Okay, here's the position functions. Here is the position function. Here is a number. Interesting. And we are interested in the captain wants the spaceship to coast into a space station. When should the engines be turned off? Okay. What should the acceleration vector be if you're coasting in? Zero, zero, zero. Right? So they're a little puzzle for you. Figure out what that has to be to make that up. Here's another one of the, here's the acceleration work backwards, and we finally had to, okay. So every question in the homework with maybe that, what speed does he need to go at to be 0, 0, 0, right? We've covered. So we're now about to start what is called the tangential and normal components of acceleration. I think I should show you a little bit. And I have a kind of confession to make. Me personally, the parts of math that I love the most, the ones I find most enjoyment, are those bits of math that nobody has found a use for. I just love math stuff because they're puzzles. And when engineers get a hold of them, they almost spoil it for me. So these things are things that engineers, mechanics, not so much mechanics, but physics people, science general, find interesting. It's called the AT is called the tangential component of acceleration. It's a bit of a mouthful. And AN is called the normal component of acceleration. Cleverer people than I have proved that, do you know that the acceleration vector is connected to the tangential and normal vectors? Remember we did tangential, unit tangent, and unit normal, remember those guys? The acceleration vector is given in terms of them. In fact, this is what they found. That the acceleration vector is a linear combination of the tangential and the normal. Can you see then that if you use as your axes t and n and b, won't the acceleration vector just be it's a bit like saying 4x plus, 4i plus 5j. It can become a very simple equation or a very simple relationship. And our job is quite mechanical. We are going to find those two guys. We are going to find, here's somebody I prepared earlier, those two guys. Now, to me, that is just plug and chug. Right? Now, this one says first derivative dot product with second derivative divided by the magnitude of the first derivative. And this one is the magnitude of the cross product divided by the magnitude of the first derivative. And I believe if you go into the book, you can actually see the ebook, you can actually see and the proof of that. There are other versions of this that do the same job. In fact, when you go and look at that question that I put online from yesterday, there are, the way I did it was just one of them, but if you go and look, there's, in the textbook, you can actually find that there's other versions of that. You can get the curvature in other ways. In fact, there is a whole connection: velocity, acceleration, and position curve, tangential, normal, binormal. They all, and curvature. All of those things interact in some really quite unique ways. So if you're interested in that kind of thing, that's what you're going to do. So I'm going to use these two formulas. You know who I'm going to start with first, don't you? I'm going to do a helix again, yeah. And that's not unreasonable, because I bet you'll probably see one of the questions in the homework uses a helix. It keeps the process manageable. And I think one of the reasons behind that is that what tends to happen in real engineering science situations is you're going to find these guys, but you don't necessarily find them by hand. Today, don't you use clever software to do it? And the argument for it is, I know how to do this by hand. It might take me, because it's such an ugly bugger, it might take me half an hour to do it, but I could do it in 30 seconds using software and we're cool. The analogy would be, I know how to multiply a 5-digit number by a 10-digit number by hand. I could do that. Would anybody in the scientific world ever do that by hand? No. But don't you need to know that so that when you do the process using software, it's not magic. It's not, this computer has been programmed to do some stuff, and I just put in this stuff and out pops this answer. I don't know where it comes from. I don't know even how they calculate it. That would not be a good place for the scientific world, right? So yeah, we suffer a little bit by doing things by hand, but that's so that we can at least say, I know what it's doing. I just don't want to spend an hour doing it. Right. So here is my space curve. 3 cosine t, 3 sine t, 4t minus 1. Usual helix, you'd expect that from me the first time. So I need to find first derivative, which in this case is going to be negative 3 sine t, 3 cosine t, and 4. I need to find the second derivative, in which case negative 3 cosine t, negative 3 sine t, and 0. Now, these formula basically use these two guys, right? And they use them in various ways. So I'm going to do the top one. So that means that I need to find the dot product. And that's going to be this guy dot that, this guy dot that, this guy dots that. So let's see what we get. I get -3 sine t times -3 cosine t plus that dot that. 3 cosine t times -3 sine t, and that times that gets me 0. What does that look like? That looks like 9 sine t cosine t, and this looks like, oh, I did not expect that. That is cool. That is so cool. Because if that's 0, won't this fella up here just be 0 over somebody and I'm done? So the dot product of the first and second derivative over the magnitude of the first derivative. Now this guy is 0. Technically speaking, shouldn't I be doing the magnitude of this vector? Can I just tell you it's 5 because I picked nice numbers, and the answer is 0. So the tangential component is 0. That means that the acceleration vector for this fella doesn't care about t. Well, let's get the other half of the process. I now need to find the cross product of these two guys. So that's going to be an I, a j, and a k. And the first fella is this guy. So -3 sine t, 3 cosine t, and 4. And this is the second guy. So -3 cosine t, -3 sine t, and 0. And according to our formula, I find the cross product, and then I find the magnitude of that vector. In fact, when you look at both these formulas, won't both these things be scalar? They will be one-dimensional objects. They will not be vectors. I mean, isn't that a term? And isn't that a term? That's a scalar divided by another scalar. And won't the magnitudes give you scalars as well? So that's going to be a single dimensional term. So let's see what we get. I get so many i's, take away so many j's, plus so many k's. Okay, where's my little pen for covering stuff up? If I cover this fella up, I'm going to get 0, take away that, which gets me +12. I'm going to get 0, take away that, which gives me +12 cosines. And when I do this one, I get 9 sine squared plus 9 cos squareds, which I believe is 9. And so the cross product of the first and second derivative is the vector 12 sine t, -12 cosine t, and a 9. Now the magnitude of that vector is going to be the square root of that guy squared, which is 144 sine squareds. This guy, which is 144 cos squareds. And this guy, which is 81. And won't these two combine and give me 144 as you'd expect? Add 81, 225, which we all know is 15. Now I've already calculated that fella and he was 5. So if you put the whole package together, the magnitude of the cross product divided by the magnitude of the first derivative, the cross product was 15, and that guy there was 5, so the answer is 3. So in this question, the tangential component was 0, and the normal component was 3. And that's the mechanics of what they want you to do. Do you know that means that the acceleration vector then is 3 times the normal vector? Don't know what the significance of that is, but evidently if you're a helix and you're spiraling, the most important vector for your acceleration is the, if you try and visualize that, can you imagine what direction is this helix going in anyway? Lost the damn thing, where are we going? Oh, it's going in the Z direction, right? So I've got a helix going like this, and this is the Z direction, right? According to this, the acceleration vector is always going to be pointing towards the center. The normal vector is always the one pointing, if you take a curve and you go, velocity vector is basically your direction vector as well. If you go right angles to that, so if you imagine a curve and you go inwards from that curve, that used to be called centripetal force? Anybody back me up? Is it centrifugal force, centripetal force? Right. So can you imagine that the normal vector is that force? Right. So for a helix, the acceleration vector is always pointing towards the center of an object. I wonder if that has any effect, or that describes a helix motion. I'm trying to imagine an object that might move in a helix way in 3D space. Why it would move that way? I can't think of a good reason why that's true, but now I know it is true. Evidently,
It'd be a person walking up a spiral staircase.
really, really fast would probably help, so that there's an acceleration vector going on. It's
Maybe
cool.
a helicopter that's lost its tail rotor.
Oh, God, yes. That would be a spiral to death. That would be a spiral downwards. At least you would know what your acceleration was. You'd be accelerating towards the center of the helix. No matter where you were on that helix movement, your acceleration vector is towards the center of it. Interesting.
Robert,
Yes.
where'd you get 5 in the last problem?
Oh, I skipped a line because I did it in my head. So let me unskip that line. Here is our derivative, and I'm saying that this guy is 5. I basically got it from 9 sine squared, 9 cos squared, plus 16, square root of 25 equals 5. I just did the helix in my head because it was dead easy.
Oh, okay. Thank you.
That's all I did. As a process goes, isn't this very much plug and chug? You find a first derivative, you find a second derivative, you do a dot product on it, you find the magnitude of that, you stick it all together, and you hope to God it's nice, which it will be if it's a helix, and probably won't be if it's anything else. You might get lucky. You might get lucky with a perfect square here or there, or something cancelling out here or there. Like we got kind of lucky, didn't we? Get a 0 out of one of them. In general, you don't get numbers for AT and AN. Do you know in general you get functions of time? Because at any given point in time, isn't the acceleration vector going to be different? A helix is a kind of special case. So I think I have enough time to talk about the next one. And then tomorrow, someone's going to tell me about it and we'll do it. Suppose I had that space curve. This would be my process. Zooming through that really quickly. Agreed? And isn't that the building block for everything else that's now going to happen? So the dot product of those would go here. The magnitude, oh, by the way, can you see that the magnitude of this vector would be 4t squared plus 4 plus 9. What would that be? It would be 4t squared plus 13, right? So you see that that actually will exist as a function of t. And if I want to get this guy, I want to do the cross product of these two guys, and that'll get me a vector. And then I find the magnitude of that vector, which is the top piece, and then it divides by that ugly guy there. What I was saying earlier is that don't you want the answer to be perfect squares and things? So that you can maybe make it a little bit prettier. But there is no guarantees, are there, that you're always going to get perfect squares anywhere. But you kind of hope that you do, because it will just make your final answer a little bit more manageable, I guess.